Okay, we will wait for 5 minutes, then we will start the session.
To 10:30, 3 hours. Good enough from the light. Otherwise, the workshop accident.
Okay, we will start with the session. Yeah, so good afternoon. welcome to the sixth session on exploring MATLAB from basics to applications. So these are just basic outcomes of the course, and so as you know, this is 3 hours course for 8-day session, and we are in the 6th session now. So today we will be dealing with ordinary differential equations, initial value problems. We will be seeing how we can solve them, and yeah, these are some of the books and references. These are some reference videos which you can refer to. Yeah, so we will begin with session 6. So initially we will, so in the previous session 5, we needed some clarification, some of the things. So we will see first that, then we will start with the new topic here. Yeah, so just clear everything. Okay, so in the previous session, the first thing which we were having a issue when we were dealing with was when we were doing the Newton-Raphson method, and we were doing it for the Lorentz system, where we had 3 different variables x, y and z, and we had a nonlinear equation there, and we were solving that using the general Newton-Raphson method, and so we were not getting the proper values was the issue that time. So the problem was with the Lorentz system. When we were solving it, we were not using the tolerance value properly. So when we were using it 10 to the power minus 6, when it converges, we should have break the total loop here. We don't need to run it up to 50 iterations. So that was the issue. So I'll just explain the steps once again. So these are the initial conditions x naught, that is minus 1 and 1 for the x, y and z variables, and we take a maximum iteration of 50, and we have a tolerance value for x as 10 to the power minus 6. That's the default tolerance level we usually take. And with Newton-Raphson, so initially we consider the vector as x naught, that is our initial conditions that we have already mentioned, and we take that as the x hold to find the error value. So we just initialized it with that. Then we take a for loop. So I starts from 1 to the maximum iteration that we mentioned, and now we have so in this Lorentz system NR function, which we have last time we have seen that. So in this function we get outputs as value and the Jacobian matrix. So in this Lorentz system, so you have a x vector, corresponding to that you have x, y and z corresponding to each first, second and third variables, and we define the output function as x minus y, 2x minus xz minus y, and xy minus 3z. These are just the normal Lorentz equations which we showed last time, and we found the Jacobian of that. And I hope you remember how we found the Jacobian. We find the dou f1 by dou x, that is the first equation, and then dou f1 by dou y, dou f1 by dou z we did, that is these 3 things. Similarly we did it for the other 2 equations. Now when we call this function for the vector x, and we saw that when we have multivariable thing, so the total vector will be the x will be a vector, and x vector minus the inverse of the Jacobian times the f. So Newton-Raphson was normal Newton-Raphson was xi plus 1 is equal to xi minus f of x by f dash of x. Instead of 1 by f dash of x, you have the Jacobian now when you are taking the multivariate variables. So that x will be now equal to x minus inverse of the Jacobian times the function. And so till here it was proper in the last time, but now we are trying to calculate the error also, or for each time, and we are checking it with the tolerance value which we have mentioned. So the error here is you have total number of rows and you have ith column. So each column it is getting updated by each time you are doing the iteration, and we are calculating the error as x minus the x old value, and the x old is equal to x is what? I think I'm talking. Okay. So the error values, so now you are having the row, each column vector you are filling the error values corresponding to the each iteration ith value, and you are storing that x as the old value next iteration. For the next iteration you are storing that x as the old value, and now we are finding the error. So we are checking that if the error value for each column which we are getting, if it is less than the tolerance value you have mentioned, we should break the loop and it should print the value. That's what our aim is. And now if I run this code, yeah, so now we know that for Lorentz equation -1 initial conditions, you should get -√3 -√3 1 as your solution, and here we are getting that -3 -√3 -√3 and 1 as our solutions. So this was the first thing which we needed I needed to clarify from the last session. So this error thing, tolerance value, and this checking the error value and terminating the for loop was the thing which we missed last time. But when you do it, you will get the proper correct answer for each of these. So that was our first clarification that I wanted to give. And then next one was using the LSQ curve fit function. How we tried it and we were getting some errors in that. So last time which we were doing was that the function example we were not multiplying with the, okay, I will explain what the problem was. So last time when we were doing it, the x data which we mentioned in the function, that is in the function example which we have mentioned here, x data was present, but last time we didn't multiply this term here, so that was making the error here. So if you multiply that x data with the phi 1, and so it is nothing but a0 plus a1 times x, and that's the thing. So x data you should be multiplying. So from starting, if you see, so these are your x and y variables you have, and we take n as the length of the x vector, and now we try to calculate the linear regression we try to use. So for that we initialize x as all ones for n rows and 1 column, and we append all the x values there, and we make the capital Y as the yth column here. Now we find the phi value. So phi value is nothing but the a0 and a1 value. So it is nothing but inverse of the x transpose into x in times the x transpose into y. So this, we saw how the linear regression thing was working there. And now for this, if we plot the thing, yeah, so you can see you have these points here, and you have a curve regression line being fitted for this. Now we were trying to, so we will just hold on that, and we wanted to, when we were trying the LSQ curve fit function we were trying, which was MATLAB inbuilt function LSQ curve fit, which we were trying. So using that, sorry, so in the LSQ curve fit function we were using, and so now we wanted to find the phi value, that is a0 and a1 is our aim to be found out. So we take phi L as our new function when we are using LS curve fit. So the function is LS curve fit. At that rate, variables x and x data are the variables here, and we call the function example. So the example function is nothing but the output value is nothing but example times the variables phi and x data. One second. So the example function will have, we have two input variables, that is phi and the x data value. So the total final value is nothing but a0 plus a1. So a0 is nothing but the phi's first value, and a1 is phi's second value, that is phi of 2 into x data. So this will give you the function example, and now we are using it into this LSQ curve fit function where we are, so we are calling that example function which we have defined, and x data we are calling it them as separate as the variables, and we are taking the range or the values up for the initial values, that is 1 and 1 we are taking, and we are calling the variables x and y. So now once you are calling these functions, and now we are plotting the new variable x and y we are plotting, and the new a0 and a1 which we got times the a05, we are plotting it in the green color. Now if you plot it, so now you can, okay, we can zoom it here. So you can see the, I will just insert the legend so that you know there are two colors. So the green is also overlapping on the red one itself. So it's giving the similar result, same result what we are expecting. So the LSQ curve fit function you can directly use using this, making the simple function, and try not to make the error that you write the function correctly so that you don't get any error like we got previous time. Yeah, so that was one more thing that we missed. We were not getting proper answer last time, and now, and another one more thing which we left last time was something like we were trying to use solve the equation using linear and non-linear regression. So that was what we were trying, and it was confusing, so we didn't do that much there. So I will just explain this with a simple example, then we can move forward in with the other process. Yeah, so what we will consider is, so what we will consider is, we will fit a model to the of the form r equal to a by b plus t to the following data, that is t equal to this time, and for that r is the measurement value, that is which you have measured from the experiments and all, and you want to know the a and b values such that you can fit using this model and you can get a curve. That's what is our regression line, that's what our aim is. So here you can see a and b is non-linear, so thus we need to use the function called LSQ non-linear function we need to use here. So what we will do first is, so since we want to use the LSQ function, we will create a function initially. So we will just create a function f error over here, and what you need to see is the LSQ nonlinear function. It actually, if I go to the LSQ nonlinear, if I do, so you see, if you see here, the LSQ nonlinear function, it optimizes the least square error of the thing. So it takes function to the square of the error. So your parameter out should be, the function output should be the error value that it checks with the, so here you can see it is the function times the square. So it actually tries to minimize the square of the error between from the regression line. That's what we need to try, and so for that our function output should be an error value that it is should be giving. So for that we define the function error, FERR we define, which is nothing but say our LSQ function we define, and we have the variable only a theta naught, a0 and a1 are our variables, or a and b are our input variables. So now we need to define the data for this. So data for the process we need to enter. So we enter, so I will just enter the, so one thing to keep in mind is we need every time, so we are doing everything with column vectors, so we try to maintain all the things as column vectors here. So now this has become a row vector, we take a transpose of it, now it will become a column vector. Similarly the ratio r also we define here the values that we just saw in the PPT. So this also we want it to be column vector. Yeah, so now we want to get the variable parameters there, so we are inputting the, so parameters we are giving. So the first input is a, that is nothing but the phi vectors first value will be a value and b will be phi times the second value in phi vector will be our b value. Now our output is, we need to calculate the error value, which is what we need as the output here of this function. So we calculate the error so the from the R model, the model answer is nothing but a dot b plus t, that is our model equation, and this is what we are planning to fit. So the f error will be is nothing but the actual R minus, that is from the already defined value, minus the R model. Now if you do this, you have you will define the function over here. Now so we will just save this function as LSQ function. So I will just save that as new folder. In the new folder I will just save it as Session-6. Inside Session-6 we have defined the LSQ function. Now we want to find the regression line for this in the using the nonlinear LSQ nonlinear function. We want to find the regression line. So for that, so for solving the LSQ nonlinear using LSQ nonlinear function, so what we need to do is we need to give an initial condition for the phi value. So phi naught will be, we consider it as 10, 10 as our initial value. Now so we compute the phi as LSQ nonlinear at the rate, so our input is p, which we are independent variable is p here. P is nothing but our LSQ function which we have defined, and inside that function we need an input phi, so that is our p value, and our initial condition phi naught if we give. So that is clear there. And now so I will just save this as Session-6. Session-6 I save it, and now if I try to run this, okay, it's saying unrecognized variable or function LSQ function, it is saying LSQ function, LSQ function we have defined. define it as LF and save it, and I will call here also LF and save. Was this the problem? Okay, it's saying the function is unrecognized. Oh, okay, the function has been saved in session. Oh, okay. But our code, this is in the, should be made into session 6. Now I think our input path was not clear. No, one second. So our LSQP we had, and we had 10Q, and LSQ non-linear function we define at P, and LSQ function we defined as LF. Okay, the file name and this name are not correct, so we save as LF we save, and now we call that function. Yeah, so now it has evaluated. So earlier the function was not properly filled, and the MATLAB path that you have given, directory path, was not inside the session 6. That was the error, that's why it was not showing that the function is not defined. Now if you see the fee values, so we had 10, 20, 30, 40, 50, and we had 0.29, 0.22, 0.18, okay, so it was 0.15 and 0.13. So we'll just save it and we'll just run it once more. Yeah, so now our fee values, you can see it is 9.4 and 22.4 were the fee values that we have. So this is the result from the using the non-linear function, LSQ non-linear function we used, and from that we got the answer as 9.4 and 22.4 as our A0 and A1 value, or A and B values, you can say. Now if you want to use the linear methods to solve this thing, so since this is a non-linear, you need to invert this equation. So it will be 1 by R equal to B plus T by A, and you can also separate it as B by A plus 1 by A into T and 1 by R. So now you have linearized it, and the parameters B by A and 1 by A are our linear parameters, and this which the errors in them is what you need to reduce using the linear least square method, and 1 by R is our y value and T is our x. So y equal to A0 plus A1x form we have brought it out, and A0 is nothing but B by A and A1 is 1 by A here. So this, if we try to do it using the non-linear function here, so I'll just separate it out here and write it as linear least square method we are going to use. So here also, as previously, we'll just take the data here for our thing. So we have the data from the previous thing, and then now we need to define y. Y is nothing but each element divided by the R value. Sorry, yeah. So y is nothing but one second. So y is equal to 1 by R is our thing, and x is equal to So we have x equal to t as our variable over here. So this was the t variable that we had in the equation here, as I have shown here. The t here is what I am mentioning here. And so you have, now we need to define a n value, which is nothing but the length of the time, so that it runs for the sufficient amount of time. And now we want to define the vector x. We initially define it as, say they are all ones, all are 1 with n rows and 1 column with corresponding to the number of time we have, and the other value will be the x, small x value that we have. Now we want to find the phi for the linear regression. So phi linear is nothing but inverse of the capital X transpose into x, x transpose into x into x transpose into y. So this was our, okay, this y will be the small y over here. And now, so we have defined the phi linear value also. Now we need to find the variables a and b over here. So now original parameter we need to define. So original parameter is nothing but a, which is nothing but 1 divided by phi linear of 2. This is how you are getting. So you are getting a 0, b by a and 1 by a as your thing. From this you are getting phi as b by a and 1 by a value. Now a is nothing but 1 by phi of 2 and b is nothing but phi of linear times 1 into a. So this how you got. This is from here. You have b by a equal to phi of 2. So you want b here. So phi of 2 into a is what your, sorry, phi of 1 into a is your b value. Now once we have defined it, and say now so we have already the, okay, so LSQ is here. I will just hold on that and we will plot the, okay, no need to plot, we will see the values directly here. So now if I clear all and I give say screen, and now if I run this thing once again, so now our once again the 1 by phi linear of 2, phi linear of 1 into a, you will get 10, 20, 30, 40, 50, 0.29, 0.28, 3, and the length of t and the capital X is 1 cm. It is inverse of x transpose into x transpose into y you have, and 1 by phi linear of 2 and b equal to phi linear of 1 into a. So you can see your a values here. A is nothing but 9.4257 and b is nothing but 22.61. So you got the same values as previous one here also. So that's how you can now solve both using the nonlinear function, and you can use the linear function also to get the unknown a and b in the equation, to get the linear regression line or to fit the model to your data which you have received. So here a and b were the unknowns, and so a and b, you are with linear method also you are getting close to similar values, 9.4 and 22.6 on one you are getting. So it's close to the older values itself. Yeah, so this is how you can use both linear and solving a equation using both linear and non-linear regression model. So I hope you can try out this thing. Yeah, so these were the three things which we missed out or we were not able to properly complete it last time. So I hope this is clear to you. Now we will enter into the next section called the, so we have seen solving the equations using Runge-Kutta second order, Euler's explicit and implicit method, and we have also seen Runge-Kutta fourth order method also. Now we want to solve this equation using the MATLAB inbuilt function called the ODE45 algorithm. So ODE45, it uses RK4 method with the adaptive step size, where the step size changes at each iteration to minimize the error that you have. So ODE45 is nothing but a RK4 it's nothing but an RK4 method with an adaptive step size, and the step size changes for each iteration and minimizes the error. So here if you have a equation of the form dy by dt is equal to f of t comma y, so the syntax for ODE45 is nothing but your t solution, y solution are your solution vectors, which that's the output values, or the MATLAB returns these solutions, y solution, for each t solution value, and you have ODE45 at the rate t comma y. So you should be careful that you are using t comma y every time, not the other way, y comma t. So t comma y you should be using, so that you get correct results over there. And you have the function name, f name. So here we define our usual functions which we did for like LSQ function and all, how we have used. Similarly, we need to define the function name here that returns the function dy equal to f of t comma y, it will return out. And you have the initial conditions t0 and tn value, representing that at y of t0 the value is y0 is the initial condition that we need to mention here at the starting. And you have the tn is nothing but the final value until which the solution is decided. Now we know how this function t f of t comma y, you can get it and all. Now we'll just try out this first, simply using ODE45, how ODE45 works. We will just first see, then we will go into comparing with other methods and all, how useful is ODE45, you can check it out. So now we are trying to solve the ordinary differential equation using ODE45. So now, so for that we need to give an initial condition. So t0 equal to 0 we are giving, and y0 equal to 1 we mentioned, and we need a t end value. So t end I am mentioning it as 5 years. Now solve the equation using ODE45 as the function we are going to use. So the syntax is nothing but the t solution and the y solution value. So it gives ODE45, and you need to give at the rate the input variables you need to mention here, and it is nothing but t comma y are the independent variables we have. And so now, so we need to mention the function first here. So we will take the old function equation, that is minus 2ty as our equation. So I mentioned that as function ODE OD for OD45 we write. It's too long, maybe OD function we write, which is function. It has variables t comma y. It has, so this is nothing but dy is equal to minus 2 into t into y. So this is our function. So we'll save this inside the session 6 as OD function we save. Now, so here we define that OD function and we give the variables t comma y with the input variables t naught, t end, and the initial value y naught. So once said that, now okay, we'll just see the syntax over here. T naught comma t end you should give. This we have closed, this we have closed, and this we have done. Function is also OD function is t comma y. Okay, then I think here we need one comma. Yeah, so now the errors are done. Then now once we solve it, we want to plot and see how the values is. Plot the function variation. So the plot is nothing but plot of t solution, and the mouse plot it. Given t solve, what is the y solution is what we want to run. So I'll just clear up everything. Run it here. Okay, it's saying t naught is undefined. Okay, it is not t o, it is t naught here. So now we will run it back again. Okay, so I have defined y0, it is not y naught. Yeah, so now we run it. Oh, it's saying the OD function has too many output arguments over here. So the OD function here which is defined, so this should be giving dy equal to OD function. So I think this should solve the issue. Yeah, so now you can see the curve going like this. So the error was we didn't define the output, how much variables it is. So it was saying it has too many output variables. It was giving out dy, 2, ty, all were giving us output variables. That's why it is, the error came as too many output arguments are there. So we need to specify which is our output argument for the function. And when we ran it, we saw how the curve is going. It started at 1 and it swapped down to the 0 at nearly 1.5 seconds. Yeah, so now set that once. Now we will try to look at another example and see how we can use the OD45 over there, and then we will look into how it can be used, or how it can be checked with other RK4, RK2 other methods. So the another example which we are going to take, so this is the equation. So we have dc by dv. So instead of x and t, we have now changed it to c and v. So c may be concentration and v may the volume of the thing, and dc by dv is nothing but minus half into c to the power 1.25. At time t equal to 0, you have the concentration as 1, and we are asked to find the c's for different values of v. 1, 5 and 10 is our rate. So now using MATLAB with the OD45 we can try to solve this thing. So solve the concentration problem using OD45 is what we are going to do now. So now for this initial we need to initialize certain things. So we know C0 is nothing but 1. Our initial V0 is also equal to 0 we take, and we need to define one more thing. So the V end until where we need to find. So we are asked to find at 1, 5 and 10 they have asked, so we will give them as the V end values. Now we need to define the V span, that is how V is varying. So V is varying from V0 to each of this V end value. So that's something. And now we are trying to solve using OD45. So from OD45 V and T we know, so it should be V solve and C solution. It should be, this should be equal to the OD45 at the rate of V comma C. These are the two independent variables we have, and now we need to mention a function. So we will define another function here. So the function, so we say concentration function, so the concentration function input variable should be V and C are the variables, and the output we need to get is the change in the concentration. DC is nothing but minus half, that is 0.5 into C to the power 1.25. So this was the equation we had, and so we need to get the output as dy, and V is dc by dV is equal to minus half into C to the power 1.25 is the thing. And so here we don't have, so we will just save it, and we give the input of this. So con function is V comma C, we say, V comma C we mentioned, and then we mention the V span value, and C0 is the value we have. Now V span is the same thing here which we have mentioned, OD45. So it is that is V comma C. Now it should be proper. Yeah. So we, with using OD45, we just mentioned the initial conditions and the span value, and for each C0 we are expecting it to find the value. So now if I clear all, and if I run this code along, the output and dy and possibly others are not assigned a value in the execution with contraction function. Okay, sorry. So here it is dy I have written. It should be dc. Yeah, and we save it. And now we run it again. Okay, we just clear everything. And now we run it. Yeah. So now if you see, for each each V solution, what are the C solution, what values is what we want to plot. So I'll just say I want to plot each V solution I want to print the column as C solution. I want to print. Okay, so we'll just put it as row vector here. Yeah, so for 1 it is, so 0 for it is 1, and for 1 liter it is 0.26243, and as this is increasing, you can see your concentration coming down, volume increasing, and your function value is coming down 0.039. So concentration decreases as your liters are increasing, the C value is decreasing as your V is increasing. So that's what we see, and we find that. So that's a simple example of how we will use OD45 in the equations. Now we want to see what advantage this OD45 has over the other RK4 methods and all we want to see. So for that, we have the function OD function. We have this OD function over here. So we will use the same equation and we will do with all different RK4 and RK2 methods, and we will compare with the results and see how different it is for RK4 and RK2 and Euler's explicit method. We will see this and we will see why RK4 method is more popular and why when OD45 you should use, and all we will see now. So I will just define here. I will define now comparison of the different methods is what we want to see. So from the RK4 method, first we will try to use the RK2 method, which we have seen. So in the RK2 method, that is Hume's method, we saw yi plus 1 is nothing but yi plus h by 2 into k1 plus k2, and here k1 is nothing but the function ti comma yi, and k2 is nothing but the function of ti plus h and yi plus h into k1. So this is what we will use for first. We will see with RK2, then we will go for the next things. So first use the RK2 method. So for this we will give the initial conditions as t naught equal to 0 we will give, and y naught equal to 1 we mention, and t end is nothing but 5. T end is 5, and so the step size we mention as 0.1 over here, and the number of terms over here n is nothing but the t end minus t naught, so 3 cap 0. This is divided by h. If you do, is what gives you a total number of things, number of iterations, and we want to initialize the solution. So for that you have capital T as t naught small step and t end, and capital Y is equal to, we initially define if them as all zeros, that is n plus 1 comma 1, n plus 1 rows and 1 column we are mentioning it. supposed to make it a vector. So our first value is nothing but our y0, which we have mentioned already. Now we want to solve this using RK2 method. So in RK2 method, so we will write a or loop for that. For I equal to 1 to n, k1 is nothing but the OD function which we have, OD function of t of I comma y of I, k2 is nothing but OD function of just copy it and paste it here. So here instead of k2 is nothing but ti plus h and yi plus h into k1 that we have mentioned previously. And if you do that, you can put a semicolon there to complete it. Now once you have found k1 and k2, now you need to have the capital Y value. So each iteration it should be increasing. So I plus 1 is nothing but capital Y of I plus h by 2 into k1 plus k2. And I give the for loop end to it. So now I have mentioned k1, k2, and I have mentioned the final y values, that is y1 plus h by 2 into k1 plus k2. That will give you the final values. Now I want to plot the results. So plotting the results is nothing but plot we want to plot is t comma y is what we want to plot here. So I'll just clear everything. Yeah, so you can see this looks similar to the plot which we solved using the OD40 files. Now you solve the same curve we are getting. Now if we want to plot the error for this, now we need to see in RK4, RK2 and OD Euler method how these things are changing. So now I want to get the error in this method. So the error how you calculate is nothing but you give the y true value. Y true is nothing but exponential of minus t to the dot square, and the error value which you have is nothing but the absolute of y true minus y. So now if the error values here. Yeah, you can see the error values being shown here, and we want to plot the maximum error value to see what is the order of the maximum error which we have. So for that we can directly write in command window max or. So the error value for this RK2 method is 2 into 10 to the power minus 3 we are getting. Now the same method, if you are solving it using the OD45, and if I try to plot it on the same graph, we will see how different it is from each of that. How each of them are different from each other. So for next we will use it OD45 method. Okay, now I will try to do the that was just our second order method which we know. And for the OD45, so we'll go with OD45 and RK4, then we'll go, that will be better. So we'll go with that. And okay, so using OD45 we want to solve this we want to do is just OD45 okay, RK2 be completed. Now we want to do the RK4 method, so that you will be having an idea of how order difference RK4 and RK2 have among each other. So now we will do the same exercise using RK4 method. Okay, so here also we will need initial condition, so we take the initial condition from here itself. We just copy that, T0 0, Y0 1, Tn 5, H has take 0.1 and Tn minus 1 will take. Then now initializing the conditions, so initializing also T is nothing but T0 plus H into Tn, 0 is n plus 1 and Y0, this is also remains same, so we keep this also here. Now we want to solve using the RK4 method, for which we will create a for loop I equal to and we are going to find k1, k2, k3, k4. So k1 is nothing but OD function of t of I Similarly, we want to find the k2 for this thing, so I'll just copy this here, copy it, ti plus h by 2 we take, h is small, so that's the time step, and h by 2 comma yi plus h into k1 divided by 2 v2 and k3 we need to find. K3 is also same thing, only thing is h by 2 it will remain same. Here instead of k1 it will be k2, and for k4 you have some changes. The OD function will be ti plus h, not h by 2, and the yi is something but yi plus h into k3. We consider. So now we have defined k1, k2, k3 and k4 for the Runge-Kutta fourth order method. Now we find the y variables. yi plus 1 is nothing but yi plus h by 6 times k1 plus 2 k2 plus 2 into k2 and 2 into k3 you need to do, plus k4 we need to take. So we have defined k1, k2, k3 and k4. We have all defined the final value yi plus 1 is nothing but yi plus h by 6 into k1 plus 2, k2 plus 2, k3 plus k4 we have seen, and we close the loop here. Now we want to plot this errors and we want to plot the graph also. So now plot t comma y we say, and same thing I need it, so we copy it. Y2 is another t square and absolute is 2 minus 1. So earlier we saw it is 10 to the power minus 3 was the accuracy for RK2. So we'll run it. We'll just close this graph and we'll run it. So we'll run this and we evaluate it. So now if I say max of the error, how much it is? 1 second. Not y not t and is high, h is 0.1 h, then I initialize that. zeros we gave and I0 we selected, and for RK4 method we have K1, K2, K3 and K4. So OD function, so and the OD function we take minus 2ty, whereas the my function here the my function value what we are going to take, one second, the my function value is minus 2ty only, yes, minus 2 into 2 into y we did. And so the session 6 is OD 44 is this thing of t of I comma y of I of I plus h into k1 by 2. And ti plus h by 2 into y of I plus k2 by 2 dih into y plus h into k3 we mounted and y plus 1. Okay, it is not getting updated into the capital Y, it should be capital Y I plus 1. This is the capital I into h by 6 into k1 plus 2 into k2 plus 2 into k3 plus k4. So I think that was the mistake. So we will just run it again. Yeah, so now the max error value we have. Yeah, now you can see the maximum error which we have is in the order of 10 to the power minus 6. For RK2 we had it in the 10 to the power minus 3. RK2 we had 2 into 10 to the power minus 3 there. Now here in RK4 we have it of the range 10 to the power minus 6, 7.47 into 10 power minus 6 we have. So you can see I hope you understood the difference now when we are doing RK2 and when we try to use the RK4 method over here. And now the standard thing was is the order of 5, it was 10 to the power minus, so 0.2 into 10 power minus 2 was the order. If you are taking, then it is 5/5 order of 5 is what we will have here, 0.7 into 10 power minus 5 you will have. Now if you see for the different methods, Euler's explicit method which we saw, the local truncation error is of the order of 2. For RK2 it is 3, and for RK3 method it is 4th order, and for RK4 method it is 5th order thing accuracy it has. But these are local truncation error. We will try to concentrate on the global truncation error, which shows the Euler's method has order of 1, RK2 has the order of 2, RK3 has the order of 3, and RK4 is the order of 4. We will try to look into this and we will see how these orders are coming and how different they are from the actual thing. Yeah, so we will go to MATLAB and we will check out for all this Euler's explicit, Rendezvous and Rendezvous method. So first we will go with plus explicit method we will try first. So for that we need to define function. So we will define three different functions. For ULS explicit we will define one function. For RK2 one function, and RK4 we will define one function. So for the first function should be, so the y value at the end should be equal to Euler function. This is nothing but it's a function of y naught t naught, that is the initial value, h is the time step, and the total number of partitions you are doing. So it is a function of this. Now we want to initialize the solution. So initializing solutions means you have the t end as t naught plus n into h, and the capital T is nothing but t naught in steps of h in steps of t end, and our capital Y is nothing but, as we did previously, is nothing but zeros from n plus 1 to 1 we have done. I of 1 is nothing but y naught. That is our initial condition that is given by the user. So once we know this, then we need to solve using Euler's method. So for I equal to 1 to n, the function fi will be nothing but define of t of I plus y of I. We have, and y I plus 1 y of I plus h into fi. Close the for loop here, and the y end value is nothing but y of end. Yeah, so we define this first function as Euler's function. So we'll save it. Similarly, we now need functions for RK2 and RK4 method also. So we'll have a 5 minutes break. We will meet at 3:25. So we were discussing about comparing the different methods for checking their global truncation error, how they vary and all. So in that thing we have defined a global function for the Euler's function. Similarly, since we have done this, we can now easily make the function for the RK2 method also. So now we will try to make the function for RK2 method. So here also, so we will edit it here, copy this and we will edit it on this. So function y end is nothing but, now it is not Euler function, now it is RK2 function we have, and we have input as same y0, t0, h and k, and we are initializing the solutions by giving the t end as t0 into n into h, and t ranging from t0 in steps of h to t end, and y values we are all initialized as zeros. Then y of 1 we take as y0. Up to here it is remains same. Now solving the using RK4 method, sorry, RK2 method. So we need to now change here. So here we will take k1, which is nothing but our function, ODE function of t of I and y of I. So this we have recently we saw how to make it, so I am just doing it once again so that you can understand how we are doing it. K2 is nothing but t of I plus h and y of I plus h into k will give you the value, and once we know that, we will find the total y is nothing but yi plus 1, nothing but y of I plus h by 2 into k1 plus k2, and we record this as y end, and this is the y end that is stored here. Yeah, so I think we will save this as our second function, RK2 function will save. So we have defined Euler's explicit function, we have defined, and we have defined RK2 as a global function. Now we will make the same thing using this. It will be far easy to make it for RK4 also, only you need to change some of the other things itself. So for RK4 function, inputs are all same and initial conditions are, these sentences are also same. Now here in RK4 method, k1 is nothing but ordinary function t of I, this remains the same thing, but k2 will now be ti plus h by 2 it will be, and y of I into h into k1 by 2 it becomes. Similarly in RK4 we have k2, k3, k4 also. So we take this and we paste it. Okay. We make k3 now. So k3 is nothing but ordinary function of h by 2 and y of h into k2 by 2 into k2 by 2 you will get. Similarly k4 is nothing but the function times h and y of into k3 and y of I is nothing but y of h by 2 into 6 into k1 plus 2 into k2 plus 2 into k3 plus k4 we will have. and this is the function rk4 function here, and we will save this also as rk4. We save. Now we want to call all these functions and compare the things with this. So for this we will now compute the global truncation error for Euler's RK2 and RK4 methods. So this array, and now for this we need to initialize certain parameters for OD. So we will just parameters for OD, so which are nothing but t not equal to 0 we take, y not equal to 1 we take, and t end we take it as 1, and the h step sizes we will try to change here. So step size will change for different values. So we will take for 0.1, 0.05, 0.01, 0.005 and 0.001 we take. So we take for 5 different values, we take the h values, and now we want to compare different methods here. So in comparing different methods, first we will take the y true value, which is nothing but exponential of minus t end square. So t end we have given the initial value here, t end is 1 we have taken, and the errors we take as zeros for have 3 rows and 5 columns we have. So we define it like that, and for I equal to 1 to 5, so our h values we take all, for each I value we will take each one. So h all we mentioned, put the semicolon here, yeah. Then we take the total n, which is nothing but t end minus t naught divided by the h value, will give you the n number of things. And now we will find the y Euler is nothing but our Euler function of y naught, t naught, h and n. So we will just end here, and we will see if it is working without any errors or not. Then we will continue with the everything. So we'll just see if, okay, we'll just clear off everything. And we'll just run it here. Okay, so it is saying not enough int arguments. It is saying y naught we have, t naught we have, h we have, and n. Euler function has OD function line 2 it is saying. Okay, OD function line 2. My function is nothing but minus 2 into t into y, and Euler function is this, and we took this Euler function. Why we are taking OD function we take here OD function of t of I. Okay, sorry, this is not TFI, this is com. I hope now this will come. So I'll just run it there. Yeah, so now okay, we saw the system is running properly. So we will plot all the things and we will check for all the things. So now we know for Y Euler how to calculate, and now for we will have three different things. So for Y Euler and where YRK2, YRK4 also we will have. So instead of Euler function here, it should be RK2 function. This should be RK4 function. And we end it. Now if we plot the values, so we plot the log of H all against the log of error value. Now we will see how we are getting the things. Okay, I'll just clear everything first. Yeah, now I evaluate. So we are getting different values for different things, and so our plot we are getting only 1 point here. So the errors we have stored it into zeros 3, 5, and our H all are saved as 0.1 and all. And why we are getting, okay, so the errors are not getting filled here. That is because, okay, we haven't defined the error till now. So we will need to define error properly. So it is nothing but 1, I for each term. It should go is nothing but our absolute of Y Euler minus Y true value. So this, once you have the error for this, similarly we will need for each row we will fill it up for RK2 and RK3 and Euler RK2. Now we should here, and here it should be RK4. And now if I try to plot, so I'll just clear up. Yeah, so now you can, so I can insert the legend over here. So the data 1 which is shown here, this is nothing but our Euler's method, and the data 2 which is shown here, dark orange thing, is our Range-Gutta second method. Similarly, the last one which is showing here is Range-Gutta fourth order. So you can see as your Range-Gutta, your slope is decreasing over here, and so the order or the global truncation of the order we can just confirm by using the so the global truncation error. How we can find is, now we just need to get the slope of that, then you will directly get into the, you can directly get the values there. So slope, I will just put it out in here itself. So say the total local error values is nothing but log of L and all. So LE I mention it as all the error values, and LH as log of all the H values. Now we want the slopes is nothing but, so we want the slopes. For slope finding we need numerator and denominator. Here numerator is nothing but all the errors times the end minus the error value for all rows substituted by the first value, and equals it. Similarly, the denominator is nothing but LH of the end minus LH of 1. If you give, now we will get the denominator and numerator. Okay, so it is saying, okay, here it should not be semicolon, it's full colon. Yeah, I think that will solve it. Yeah, so now you got the numerator and denominator. Now the slope is nothing but numerator divided by denominator. If you do, we will get the slope values, and you can see the slope for the Euler's explicit method is 1, and for the Runge-Kutta second method, RK2 method is 1.99, it's approximately 2, and for RK4 method it is of the order of 4. So this is what we were mentioning here. So the Euler's method is of the order of 1, which we saw here. Similarly, for RK2 we have the order of 2, which we got from here in the slope, and for RK4 method it is of the order of 4, which you can see from here. So that's why RK4 method is pretty famous, due to its high order accuracy when compared to the other methods. So I hope that is clear for you. Now, so we saw that RK2 method is higher, second order accurate, and now we need to, so we are going into a section called multivariable ordinary differential equations, where we try to apply these multivariable differential equations what we have learned, ODE solving and all, into multivariable cases, and we will see how to solve the stiff ordinary differential equations, and some practical examples we will see first. So first we will see an example of a damped spring mass system. So those who don't know, are not aware of this, so in a damped mass you have a mass over here, and this is the spring that is connected, and this is the damping thing that you have. With spring has a constant of spring constant K, and we have a mass M, and the damping coefficient is C, and you can write a second order equation of the form md square x by dt square plus c dx by dt plus kx equal to 0, and for a given initial condition at x equal to 0, at t equal to 0, x is equal to 1 is the initial condition you have. Now we need to convert this second order equation into two first order equations to solve the problem. So for that we can write dx by dt as v, that is dx by dt is nothing but velocity, so you can write dx by dt as v. Then you have m dv by dt plus cv plus kx equal to 0. So at t equal to 0, x is equal to 1. Similarly at t equal to 0, then v will also be equal to 0. Now once you have this, you can now write it into a matrix form with y, small y as the vector of, this is nothing but our psi, and this is nothing but x and v are now the variables. So dy by dt of y is nothing but v, that is the right hand side, and minus this, if you bring it to the right, it will be minus CV plus kx by m. This will be our matrix thing. Now we want to solve this ordinary differential equation. Is first order equations. Now we have the initial at t equal to 0, x of 0 is equal to 1, v of 0 equal to 0. We will take m equal to 10, c equal to 5, k equal to 15, and until time t end as 10 here. We will change this damping coefficient and we will see how the curves vary also. So we will see that in MATLAB first. So we will close this. So I will just clear up everything. Okay, so we'll make it into, and now we want to solve the function of mass spring system. So this set of ordinary differential equations will be solved. So we will be using OD45 for solving this. OD45 we will use whatever we use to solve the OD45 to solve the equations. So for which we first need to define one more function for this mass spring system. So we define a function as, so the output is value, it is nothing but mass spring function we define. So the mass spring function is nothing but it has variables t and y. And now x is nothing but y of 1, v is nothing but y of 2. And we need to define the constants here. So we are defining the constants. So c is equal to 5 we will take, which is mentioned in the book. So it's a PPT which we have seen. So k equal to 10 we have, m equal to 10 we have, and then we define dy by dt, which is nothing but value of 1 comma 1 equal to v, and value of second row first column we mentioned that as this is nothing but our minus of c into v plus k into x value whole divided by the m. So minus cv plus kx by m is the value that you will get. So now we have defined the function over here, so that now we can directly call this function and do the OD function over here. So we will save this as mass spring function and we will now use it here. So for this initial we need y naught initial value. So we mention y naught as 1 and 0, and we mention the t span value as 0 to 10 we will mention, and we will now solve it. You will see we will solve using OD45. So we have the syntax as t solution y solution is nothing but OD45 @ t comma y ms function t comma y. We have t span of, and we have y naught as your initial condition. Now we put a semicolon to it. Now we have t cell. Okay, we need a comma here. Now that will be good. So once we get it, we want to now plot the output. So for plotting output, we will directly plot the t solution comma y solution from first x will plot. Yeah, we will just run it. Yeah, so now you can see this is an underdamped condition where c equal to 5, you are getting the thing damping out. Once a certain oscillation, it is quite damping out. Now I will just type hold on, and inside here we will change it to a 50, which is more damped condition, and we will just run this, on which now we will run this again, and now you can see this goes like a straight line. It gets saturated to 0 very nearly without any oscillations. Now we will run the same thing. Hold on will run, and we will now change it to on some oscillation state where damping coefficient is very low, and if we run that, yeah, so now you can see the orange color, it is having a lot more oscillation compared to the other things. So these are the three things how for a multivariable case how you can plot the solution. And if we see this, with the RK4 method also you can do the same thing. With RK4 we will see the, okay, so we can run the same thing. Just close it here, and we can see that we can run the same OD functions and all. So for this, so we have already mentioned, so we'll just maintain it here 5. We have already mentioned all the initial conditions. So we will take the Runge-Gupta function. So we have mentioned all this. T is not 0, so we have mentioned, and all. Only we need to mention the initial condition, and then we can take the RK4 function from here, and we can solve it. Instead of OD function, now you need to use the spring mass function over here to solve that. That's what the change you should do when you are doing this. So we will take this, copy it, sorry. So we will solve the OD. Using RK4 method also. It is RK2, it is written to show RK4. Okay, so we will make the function using the RK4. So for this, function is already, we need just the initial conditions. So y naught is something but 1 comma 0 we take, t0 is equal to 0 we will take, and t end we want to go up to 10 seconds. H we take normal 0.1, and n is nothing but t end minus t naught divided by h. We will take, and we will initialize the conditions. T end is equal to t naught plus h into t, and we take, so we want to make it a column vector, so we take the transpose of it, and we make the zeros initial conditions, and one. Now we will make it a row thing. First all rows, first column is our y naught. Since it's a multi-variable now, we need to make different input values, and here in before the RK4 we need to use yi is nothing but capital Y of all the rows, y should be there. Then k1 is nothing but now ms function di comma yi. Then just replace this with ms functions, as our main function has changed, so we need to change that here also. So now once you change that, you will get the y value now. So say you want to put small y over here, y new we have, and we will update this y new every time into the capital Y thing. As y new we will enter it up, and we will close the loop. Now our final output and plots if you do. So y end is nothing but y of all the row up to end, and we plot. So if we now plot it, so we will just run this first. I'll just clear all. CLC video, and we try to run it. Oh, okay, 1 second. The capital Y is just run this thing. Is this the color? No, this is is this the that is also done. This is not needed here. So the assignment is somewhere 10 T naught, T end is 10, H is 0.1 and N is T end minus T naught by H, and we give T is T naught into H into T end and zeros. It's again showing unable to perform the assignment because the size of the left side is 1 not 1 cross 1. It's 2 by cross 1. 2 cross 1. Okay, so y naught is 2 cross 1. And the assignment that is performed here is T and y. Is getting updated and 2 cross 1 is nothing but y naught. F1 is this the thing that is. Okay, so this is the error point where we are getting. So the y's we initially define them as zeros, 1 not 1 rows, 1 column we have defined, and the first column all rows is y naught we have defined. This should get updated by each of this thing. Second column should be okay. Here y should be not n plus 1 comma, it should be 2 comma n plus 1, 2 rows and first n plus 1 columns. It should. Now I think this will make sense. Function index must not exceed 1. Line 3 it is showing error. So mass function x is nothing but y of 1 and v is nothing but y of 2. Small y has 2 rows and 1 column. 2 rows and 1 not 1 columns it has. And now it's saying index exceeds the number of array elements. Y value, y we got it from function and ms function y of 1 y. So we have 2 y values initially. for this transpose it should be taken, and 2 rows and n plus 1 columns it is having, and it is showing an error of index must not is one will not be the correct one, because we have two things. Do not touch to the end. Zeros we have, then by 1 is equal to y naught 1 to end, and okay, I'll just check it out why this error is coming. So this will also, the RK4 method also will be giving some similar results that we got for the OD45 things itself. It will not be having much difference range, because RK4 is much having 10 to the power minus 4 of the global penetration error order it has. So it closely matches with the OD45 thing. So that's what I wanted to show with this program, and we will see the difficulty of applying OD45. As it is RK4 method, it becomes difficult to solve we will see something called stiff equations, which are where OD45s become little difficult to be solved. So at that time we need to use some other OD functions to solve those problems. So we'll just see what are stiff functions initially. Yeah, so stiff functions are nothing but you have different scales, that is you have some fast scale and you have a slow scale. So when you have ordinary differential, x1 dash is equal to minus 100 x1, the amplitude of this is 100, whereas if you have another equation of the same form, but now the amplitude is 0.01, so this moves very faster, so it will take h very small values, but this is itself is small, and if you take both of them are constituting in the same as a coupled equation, then the h value is significantly low, and this second equation needs to be run for larger time to get to the convergence. So this takes OD45 cannot do this kind of changing thing, so it needs some other function, for which we have something called OD15s, where this kind of changing the h according to the requirement for different fast and slow scales will be adjusted using this OD15s function rather than the OD45 function. So we will take the first stiff equation, x1 dash is equal to minus 100 x1 and x1 of 0 is equal to 1 as our initial condition, and if we go to MATLAB and just clear all now, and if I run the OD code on that, so this is tsolve y solution is nothing but OD45 at the rate of t comma x minus 100 times x, you will have 0 to 1, 1 will have, if I solve it now, if I try to plot this t solution against the x solution what I have, oh sorry, it is not x solution, it is y sol. So it will plot it. So now you can see this 100 function and the amplitude when it was 100, your curve came to 0 within very small function, 0.1, within 0.1 within 0.1 itself it came to the 0 value. Now if we run the same function with the other, only the amplitude, if you change it to 0.01, and if you run this for 0 to 1 second, and if you plot this value t solve comma y solution, if you plot plotted it on the same thing, t solution comma y solution, we have t comma x minus 0.01 into x comma 1, and plot say few. Okay, before that I think I should clear all, and I run the code once again. Okay, so it is now t comma x and x, if you are having, this remains, it should be remaining constant, instead it is okay, it's okay. So this is nothing but, this is actually the value staying at 1 only thing is the plot values are these are restricted to this. So if I restrict it to 0, now you can see this line, it remains at 1 every time. If I make it thicker, you can see the line every time stays at 1. It has not changed much and it has not converged till now. Instead, if I run the same code for, say, from higher value, say from 0 to 3000, if I run, and if I plot this same thing, now you can see at 3000 it took, for that small amplitude to come to the convergence 0, it took 500 points. Earlier it was very low, 0.1 and all. Now it took 500 seconds to come to this lower convergence thing. So when you are having 100 here in the amplitude, so the system responds very quickly, whereas when you had a smaller value, 0.01, when you had, the small system responds very slowly. So this response of the system changes, and if you are having both of them in a single equation, that as we mentioned here, if we are having both of them in the same equation, we call these kind of system of equations as stiff systems, where you have two different scales, slow and fast scales, present in the same equation. So when you are having 100, you need to take a very small step, 0.001, but as you are going to 0.01, the step size, since it takes 0.01 here, it will take this same value here, and it will continue to, it needs more time for you to evaluate and converge. So for this particular function, minus 100, 0, 0 and minus 0.01, we will see how to get the curves, how we get the curves and how we can solve it. So I'll just plot this here, and we'll just write one more function for this. Multiple variable function, t comma y we write, function matrix A as minus 100, 0, 0, minus 0.01, and the value is nothing but A into y we have. So we save this multivariable function as MV function, and now if you call the same function over here, tsolve, instead of OD45, instead of this simple function over here, we will write this as multivariant function t comma y we will take, and we will run it for 0 to say some 200 value with the initial condition of 1 comma 1. Okay, it's unrecognized function, small y it is saying. Small y we need to bring it from the max function of a into y. Small y is nothing but x1 and x2, and x1 x2 is nothing but, so the x1 x2 terms give the small y value, and the small y is the variable over there, and the value out is nothing but our function times x1 and x2, and x1 and x2 initial values so here I give the function as x, it should be y here, then it should be, okay, now that was the problem. And if you see here, it took 2 lakh steps for it to converge to this particular value, and if I plot it, t solution comma y solution, you can see this one of them is a fast variable, that is this blue thing, and the other is a slow variable that takes a lot of time. Even at 200 it is not converging. So this kind of slow fast dynamics when you are having in your system, you need to consider all these equations. Now instead of OD45 we have another equation set of this thing, same thing, just only thing will change is the solution equation as OD15s we say, and we will run it, and we will plot this also we plot the thing. Now you can see it converged within 88 times, 88 steps it got converged to the same answer. So when you are doing OD45, for higher steps it took when it started initially, it takes low steps of 10 to the power minus 4. So you can see the time step. Initially it took 10 to the power minus 4, then it slowly progressed. In OD14 it takes 10 to the power minus 2, it came, then it came to 10 to the power minus 1, and then it came to 10, and then it went to 100. So these different things. Once the x value converged, OD15s takes a bigger step to get to the required value, and that makes the system more faster enough. Within small time steps it is able to calculate the same functions as we know. So OD45 should be used if your OD45 should be used initially, and if you are not able to get any convergence or it is still pending for a long time, then you should be using OD15s as your solver. Now if you have the same, say some other function of the form minus 50, this kind of form is there, we'll see we should use OD15s or OD45. We need to check it. So for that, so in our my MV function value, we need to change this equation. So we have is 5.7, 1.85 we have, 13.2 we have, and minus 4.3 we have. So this is our new A. So we save it, and then now if I run the plot 45 initially, and with the function up to 0 to 200 in one step, it's showing a multiplication. Star is not duplicate. Minus 5.7, 1.85, 13.2 minus. Incorrect application. OD45, iterate t comma y. MV function of t comma y we want 0 to 200. 1 to 1 we need. A into y we had. Yeah. So the value is something but A into y we did. In the matrix, I check the number of columns and number of rows in each matrix it is. So that means there is a mismatch in the list. Okay, here also the error is there in A into y. Okay, so here this should be semicolon. Yeah, sorry. This is first row and this is second row. Now I think it will look just clear everything. Yeah, now you can see it took 2429 steps to reach to this. Now we will run the same thing with OD15. OD15 as we will run. Now you can see it took only 40 steps to converge to this. So this happens because the A matrix, this happens because if you see the eigenvalues of the A matrix, so I will just copy this here. Now if you see the eigenvalue of A, you can see it is minus 9, minus 10 and minus 1.01 it is. So the ratio between them, if you take, say, ratio is nothing but answer of 1 divided by answer 2 if you consider. You can see it is of the ratio of 1000, 1.1 into 10 to the power 3. It is of that ratio. So it is the eigenvalue ratio is very high. So this is the reason why you are getting to very low steps for very high steps for the OD45, and you need more number of iterations in OD45 compared to OD15s, where you are taking only just 40 steps to converge to this. Similarly, so this is one implicit, it's an implicit solver, so OD15 can take these things, whereas OD45 is a Runge-Kutta solver with an adaptive size h, but it has limitations on this kind of stiff equations. Now we will take one more example on a nonlinear example from a nonlinear dynamics called the van der Pol oscillator. So its equation is x double dash, this is nothing but square second order d square x by dt square, it is minus nu times 1 minus x square into dx by dt plus x equal to 0. At time 0, x is at 2, x dash is at 0, it is showing. Now he is asking us to consider for 1 and 100. So nu is nothing but the damping thing. He is asking us to take for nu equal to 1 and nu equal to 100, how the system varies when your damping is changing is what is being asked of us. Now so for this we will just create a function to call the van der Pol equation. So we have a function, say value is nothing but van der Pol oscillator t comma y we have. So you have the value for nu as 1 in given, and x is equal to y of 1, v is something but y of 2, and you have the value of 1 comma 1 equal to v, and value of 2 comma 1 equal to nu into 1 minus x square into v minus x. So this was the equation given. Now if I just and CLC, now if I just run the OD45 over this, I'll just need to change the function over here. This VDP, I need to save this, save it as VDP. Now we will say run it for 0 to 10 seconds, and with an initial condition say 2 comma 0 take. And now if you run it, and then if you plot it, so now is how if you plot it. Okay, so it took this. Yeah, you can see this small and fast variation happening here. It is the blue thing is what is going, and it is coming up like this. Now if you so now this was the case when nu equal to, when our new value was 1. Now if I make it into 100 and I save it, and if I run the same thing here, so since it is higher we need to give it for larger time. So if I do that, you can see it took 2.18 lakh steps for solving it. And if I plot the function, I plot this, so you can observe this. say nu equal to 100, y equal to 1, y equal to 2, we had okay. So when OD45 worked with VDP at t comma y for 0 to 1000, we got for 2.1 lakhs, and your curve goes somewhat like this. Whereas if you run the same thing for OD15, yes, if you run, you can see that it converged within 1717 itself, 1000 itself, and the plot function, if you do, you will see the same result as here. So, but it converged it 1717 steps itself. Now, if you increase the nu to say some higher value, 1000, and you save it, and if you call this function, so we just call it. First I will just see for OD45. So you can see OD45 is running, and it took some 2.23 lakhs steps it took for it to converge. Whereas now if I take 15s, OD15s, it just took 227 steps to converge. And if you plot this, okay, the figure is not exactly proper. So basically we wanted to show us the OD15s you need to be using when you have stiff equations. When your OD45 is not working properly or is getting very high values of these things, then you should be using OD15s for your solving. Just see the figure is not the figure is not absolutely correct, but the concept which we wanted to clear was that when to use the OD15 thing. Now for the final section we want to talk about is something called how to transfer your partial differential equations to ordinary differential equations and then solve it using these functions. So there is a method called method of lines for transient partial differential equations. So if you consider a simple rod and you have one end being heated at 100 degrees centigrade and the other end maintained at 25 degrees centigrade, that is at atmospheric temperature if it is maintained, and it is uniformly heated at Ti equal to 25 degrees centigrade. So this partial differential equation you can break down that this d square t by dx square can be written using the central difference formula as Ti plus 1 minus 2 Ti plus Ti minus 1 by delta x square. And delta x is nothing but the h by n, how much time you have splitted it into the 1 by nth thing, n number of things you have splitted it into different segments, that is the delta x value. So you can use the central difference formula here and you can now make the equation into a ordinary differential equation. dt by dt is alpha times Ti plus 1 minus 2 Ti plus Ti minus 1 by dx square. So for a t1 of 100 and tn plus 1 of 25, the solution vector of T2 to Tn different temperatures you can find using the ordinary OD45 itself. So we will finish that for today, and so we define the function value is nothing but rod function we define as t comma y. So here you have parameters like TA equal to 25 and temperatures, you get this n equal to length of y plus 1 and t of 1 is already given to us. T of 1 we take it as 100, then T of 2 to n we take it as y, and the T of n plus 1, the term, there is a final value also we know, which is nothing but the ambient temperature that we have, and the H value is nothing but 1 by capital M. Now we define the dt over dt. So dt over dt is nothing but zeros of n plus 1 from r for I equal to 2 to n dt over dt of I, or your measure is nothing but you can directly write it as alpha. We haven't defined the alpha thing, but we can okay, so we'll put it here and we'll have h squared into t of I plus 1 minus 2 into t of I plus t of I minus 1 minus beta times t of I minus t of A. And we close this thing. Now we need to have the values of alpha and beta, which alpha is equal to 0.025 and beta value is 0.1. So now we try to get the value of dt. This is nothing but f value equal to dt of dt okay, it's not f value, we define it as value. Now, so we save this as a function. So rod function we saved. Now okay, I'll just put it here. So now for conduction problem, so initially n equal to 10 will define number of steps and t naught as 1 is equal to 25 and this is 25 and t naught at n plus 1 not 1 is 25 and solving the ODE t span as 0 to 20 I0 equal to t0 to 10 and we diffuse the ODE function t solve y solve as OD45. We use the OD45 to solve it. T comma 5 instead of PDP we use plot function. T comma y and this is nothing but the t span which we have mentioned and this initial condition is nothing but y naught which we have mentioned here. Now if we try to run this, if we see any errors, okay, so now we want to plot the t solution against the y solution value. So we will run this. Yeah, now you can see. So this is the cold region and this is the hot region, and you can see how it different. Near to the cold region it is 20 and as you go towards the hot region you are at a temperature of 90 and all. So this is how the temperature distribution for each positions you can get the temperature. This is what it shows, and so this is colder region and this is the hotter region of the plate rod, and how the temperature varies for each given distance you can see. Now if we want to plot these particular things at say n equal to 100, we want to plot for that n equal to 100. If I want to plot t sol comma y sol at n by 2, half of the thing, n equal to 100 t sol y sol all rows and n by 2 we wanted. Okay, y sol we are getting is transpose. Okay, so our y solve is having 9 cross 285. So all the rows, and we wanted to plot at that particular value. So we will take, I will say y sol equal to y sol transpose C, and then you plot the function. Okay, then your T solution should also be a transpose. Transpose we make, and then you plot the thing. Cross 85, and this is at 9 cross 85, so we need to plot the T solve at 1, and this is at, say, first row I want to plot. Okay, that comes to a particular single value only. Instead, if I want to plot it, okay, so when we run this, we got this. Instead, if I put n equal to 100, you can see the variation there, and we specifically want to plot at T solve at all now, and by 2 we wanted to plot. Yeah, so you can see the parenthesis was missing, that's what the error showed. So at half of the thing you can see the temperature, how much 50 degrees it is showing. Now if I want to go very close to the thing, then you can see this is at, and there is 100 by 10, that is a 10th value you can see. Now if I go at now you can see the temperature reduced to 30 degrees centigrade. So I will just plot this. I will just clear all, and I will plot this one first. I should run this first. Now I should plot curve like this. Now I put a hold on, and then I plot simply n by 10 over the equal span, and I'll put one more hold on, and I'll plot it for very close to the, yeah, now you can see how the temperature varies when you are very close to the 25 degrees, that is atmospheric temperature, and you are going far towards the hottest temperature. You can see how the temperature varies at each particular location of this rod using at different positions, you can see. So this is how you can use ODE functions for solving the system when you are required it. You don't need to solve it every time. You need to use the OD15s at particular locations where you don't have the option, and you feel like it's the solution is not converging within a definite distance and all. Otherwise, OD45 is far better to solve the things. But you need to be, if you know if it is a stiff equation and or not, then you can directly use OD15. Else you need to first try with OD45 and see if it's converging or not. If it does not converge, then you need to use the OD15 to solve the equation. So I'll just